Hey guys, in this video we will be reviewing gas laws and how to solve problems with them. So before we get into some problems, there's a couple of just pieces of information that you need to know. So the first thing is standard temperature and pressure. So you need to know that standard temperature is 0 degrees Celsius. But you remember, in gas law problems, we can't usually use Celsius. We need to always use Kelvin. So 0 degrees Celsius is 273 Kelvin. And we'll talk about how to convert between Celsius and Kelvin in just a second here. And then standard temperature is 1 atmosphere, so 1 ATM. So if a problem tells you it's done at STP, then that means 273 Kelvin, 1 ATM. Okay, if a problem gives you Celsius and you need to convert to Kelvin, you need to just remember that Kelvin is Celsius plus 273. So degrees Celsius plus 273 to get to Kelvin. A couple other conversion factors you need to know is that 1 atmosphere is the same thing as 760 millimeters of mercury, mmHg. That might be a conversion you might need to know. Also, 1 liter is 1,000 milliliters. Hopefully you've got that one memorized by now. And then one last conversion factor that's useful to know is that if a gas is at STP, 1 mole of that gas will always take up 22.4 liters. Now, that's only true at standard temperature and pressure. So if the gas is at 273 Kelvin and the pressure is 1 ATM, if it's any other temperature or pressure, then the volume is going to be different. But since a lot of problems happen at STP, this is something that's kind of useful to know. So this is a conversion factor. It can help us solve this problem down here, which says how many moles are in 50 liters of oxygen, which is a gas, at STP. So since we're at STP, we can just go 50 liters, make a conversion grid thing, and then we know 1 mole of O2 would take up 22.4 liters at STP. Then just cross that out. We have 50 moles of O2 divided by 22.4, and that will give me 2.23 moles of O2. Now, if you forget this conversion factor, you actually could solve this problem using the ideal gas law, which is PV equals nRT, and you could plug in your standard temperature and pressure into this equation. So your pressure would be 1, your volume would be 50 liters, N is the number of moles, which is what you're looking for. R is that special constant that's 0.0821, and your temperature would be 273. And you could solve for X and you would still get 2.23. And we'll review how to use the ideal gas law in just a second here. But just wanted to point out there are multiple ways to do problems. Okay, the next thing you need to know about gases is what we call the combined gas law. So this is our P1 V1 over T1 equals P2 V2 over T2. And we can use this when we have a situation where the pressure is changing, or the volume is changing, or the temperature is changing. Just a reminder, as always, your temperature must be in Kelvin. Even if they give you both your temperatures in Celsius, you gotta change it to Kelvin. Your pressure and volume, they can be in whatever units you want, which is kind of weird that these ones can be in whatever units you want, but temperature has to be in Kelvin. So let's read this problem. A sample of gas has a volume of 400 liters when its temperature is 20 degrees Celsius and its pressure is 300 mmHg. What volume will the gas occupy at STP? So lots of stuff going on in this problem. Let's break it down. Let's figure out what all of the different parts of our equation are. So we should have all of the numbers except for 1. and that will be our variable. So let's see, our first pressure is 300 mmHg. And again, in this equation, I don't have to change my mmHg to atmosphere, so I'm just going to leave it. If you really want to change it, you can, but I'm going to leave it. The volume is 400 liters, and the temperature is 20 degrees Celsius, but I need to change that to Kelvin, so it's going to be 293 Kelvin. Okay, now it looks like I don't have anything else, but look, it tells me the gas is going to be at standard temperature and pressure. So I know standard pressure is 1 atm, which is 760 mmHg. So my pressure is 760 mmHg. The thing with the pressures is that they have to be in the same units. So I can't have this one be mmHg and this one be atm. They've got to match. The volume, we don't know. It's asking for the volume, so that's going to be X. And then our temperature is going to be our standard temperature, which is 273. Okay, so now I've got a bunch of numbers. I can just plug them into my equation. So it's going to look like P1, so like I'm plugging them into here. So P1 is 300, V1 is 400, T1 is 293, and then P2 is 760, and then V2 is X, so you can either put X or you can put V2, like whatever you want, and then T2 is 273. Okay, so what I would do to solve this is I would multiply this top of this fraction by 273 and this top of the 760x by 293. This is like cross multiplying. You multiply those two, and those go on opposite sides of the equal sign. So when you do that, you end up with 273 times 300 times 400 is a really big number. It's 32,760,000. I calculated this in advance. Don't worry, I'm not doing this in my head. 293 times 760 is 222,680x. So this number is 293 times 760. This number is 273 times 300 times 400. You can also think about multiplying both sides by 273, which would just cross out on this side, and then you'd end up with 273 on here. And then multiplying both sides by 293, which would just cross out over here, and then you'd multiply by 293 over here, if that makes more sense to you. Anyway, however you get to this point is good, as long as you get to this point correctly. And then to find x, we just divide by 222,680. So that cancels out right there. And then when you divide these two numbers, you get x equals 147 liters. Okay, so I know there's a lot of challenges with this problem. There's reading the problem and figuring out what the numbers are. There's doing the algebra. If any of these are hard for you, come talk to me and we can work on it. But hopefully that makes some sense. Okay, next problem. Using the combined gas law again. A sample of gas has a temperature of 100 degrees Celsius at 95 atm. What is its temperature if the pressure is increased to 200 atm? Okay, so again, we can tell that we need to use the combined gas law when we have a gas that is changing conditions, like it's going from one pressure to another pressure. Or in this case, it was going from several different things, a different volume and a different temperature and a different pressure. Like all of those things were changing. Okay, so our full equation is P1 V1 over T1 equals P2 V2 over T2. Now this problem only talks about temperature and pressure. So if it doesn't mention volume, we can just ignore that and assume that it's constant. Sometimes it will say the volume is constant, sometimes it just won't say anything about it. Either way, if it's not mentioned, just ignore it, cross it out. So that means our equation, instead of being P1 V1 over T1, becomes just P1 over T1 equals P2 over T2. That makes this problem a little bit easier, because now we just need to figure out 4 parts of our equation. So our first pressure is going to be 95 atm. Our first temperature is going to be 100 Celsius, but I need to convert that to Kelvin. So that's going to be 373 Kelvin. My first pressure, or my second pressure, is 200 atm. And my second temperature is what I'm looking for, that's X. Okay, so when I plug this into the equation, I get 95 over 373 equals 200 over X. So, a couple ways of solving this problem. You can do the cross multiplying thing like I did. So X times 95 is 95X. 373 times 200 is whatever that answer is. And put that on opposite sides of the equal sign. Or something else you could do is divide, and I'll do it this way this time, divide 95 divided by 373. So that equals 0.2547 over 200x. And then multiply both sides by x. So if we multiply by x over here, my x's go away. And then if I multiply by x over here, now I have 0.2547x equals 200. So I just need to do 200 divided by 0.2547, and I end up with x equals 785 Kelvin. And with these kinds of problems, we always want to stop and make sure it makes sense. So I've got 373 Kelvin to start with. I'm increasing the pressure. Does it make sense that as I increase the pressure, the temperature would increase? And it does. If you're thinking about it, it should make sense that the temperature would go up quite a bit. So that answer makes sense. Okay, last thing that you need to know is the ideal gas law. So the ideal gas law is the one that looks like this. It's PV equals nRT. And with the ideal gas law, there are specific units that all of these pieces have to have. So with the combined gas law, our temperature had to be Kelvin, but our pressure and volume could be whatever we want as long as they match. Not the case in this one. So I'm going to go over really quickly what the units have to be. Pressure has to be in atm. Volume has to be in liters. N has to be moles. R is a specific number. It's always the same in every single problem. It's 0.0821. And there are some units to that number if you're curious. It's atmospheres times liters over mole times Kelvin. And then your T has to be in Kelvin. So they could give you any number of different units and you'd have to convert. Like they could give you mmHg and you'd have to convert to atm. Or they could give you milliliters and you'd have to convert to liters. Or they could give you grams and you'd have to convert to moles. Or Celsius and you'd have to convert to Kelvin. And they might not, but they might. So just be aware of that. Okay, so here's an example of that type of problem. A sample of nitrogen gas has a volume of 5.56 liters at 0 degrees Celsius and 1.5 atm pressure. How many moles of nitrogen are present in this sample? So you can see that the nitrogen gas is not changing. So that's how we know we don't need to use the combined gas law. We just want to know the moles at this particular instant. So let's go through and figure out what we have here. So they gave us a pressure, it's 1.5 atm, and that's the correct unit, so we're good. They gave us a volume, 5.56 liters, so that's the correct unit, so we're good. N is what we're looking for. We're looking for number of moles, so that's going to be X. R is going to be that same number from before. And our temperature is 0 degrees Celsius, but I have to change that to Kelvin. So 273 Kelvin. All right, so now I've got this all figured out. I can put it into my equation, which is PV equals nRT. So my pressure is 1.5. My volume is 5.56 equals X times 0.0821, and my temperature is 273. Now if you want to, you can put all the units in here and they will all cancel out and it's all really nice. Just to make this super quick, I didn't do that. So now there's a couple ways you can go about simplifying this. I'm going to just multiply 1.5 times 5.56. It gives me 8.34. And I'm also going to multiply those two numbers together. So 273 times 0.0821 is 22.413x. And then if I want to get x by itself, I just divide by 22.413. So x is going to equal 8.34 divided by 22.413, which is 0.372, and that's moles of N2. All right, so that is gas laws and using the combined gas law and the ideal gas law. So lots of stuff to remember there, but I know you guys really can do this algebra. Again, if you're struggling with the algebra or with reading the problems, come talk to me and we'll talk more about it, but you can definitely do this.